In this video, I want to talk about the idea of projecting one vector onto another vector. And I'm going to present this with an example where we're trying to project this green vector, -1, 3, onto this blue vector, 2, 4. So first off, what does this even mean? Well, when we're talking about projecting one vector onto another vector, we're really talking about projecting it onto a line determined by that vector. So this blue vector, its span is a line in R2. And so really I'm talking about projecting the green vector onto this entire line. So the blue vector kind of only exists in order to define this line. And when I'm projecting onto a line, I'm asking what's the closest point on the line to my vector? So what's the closest point on the purple dotted line to this green vector, or really the end point of the vector, right? We're thinking of the vector as a point in space. Now, to figure this out, I can drop a perpendicular line. So this orange dotted line is perpendicular to the purple dotted line, and that will define the closest point on the line, which if I draw as a vector, it's this red vector here. And we can see that this projection is the point 1, 2. So that's what it means to project a vector onto another vector. We look at the span of that vector, which is a line, and we ask ourselves, what's the closest point in that line to our vector? And to figure that out, we drop a perpendicular line to it, and that's the closest point. Okay, another way of thinking about this, because I think this is useful to understand what's this term projection saying, is we can think of this as a shadow. So if we were to take a light source really far away from our vectors and kind of shine it in the direction of the purple line, what would happen was that the shadow of our green vector would fall where the orange vector falls. And so what we would see as a shadow is this red vector. So this is another way of thinking about what projection means. And projection shows up in all sorts of situations. One that I'll just briefly mention, and I won't really work out an example, is if you've taken any physics classes, when you're trying to figure out if you have some force applied on an object. Let's say you're trying to push an object up a hill, but you're not pushing up the hill. You're just kind of pushing horizontally, and the object is moving up the hill. If you wanted to figure out how much force is being applied in each direction, that would boil down to projection. Right? You're thinking of the force you're applying as a vector, and the direction in which it's moving, the object, is the line onto which you're projecting your force. So there are lots of physical and non-physical situations in which projection is useful. And so what I want to do in this video, the main goal, is to figure out, first of all, why this makes sense, or two things. Why this makes sense in higher dimensions, and also how do we come up with this answer? How do we get the number 1, 2 without actually working this all out? And so first of all, let's figure that out, or I'll give you the formula. How do we figure out the projection onto a vector without actually visualizing it? Because in higher dimensions, we won't be able to do that. So the formula, I'm going to call this thing, this is V and this is S. What I'm talking about then is the projection onto S of V. And there's a really nice formula for this, and we'll work it out in this example. It's given by this. We take V dotted with S, which will be some number. We take S dotted with itself, which will be some non-zero number because S can't be 0. Otherwise, this whole setup doesn't make sense. And then we multiply this constant by the vector S. And let's be careful here. These dots are dot products between vectors. This is a scalar multiplication, taking the constant that we get and multiplying it by S. And so what do we get here? Well, what's V dot S? Well, when we dot these two vectors, we get 10. What's S dot S? Here, S dot S is 20. And what's S? Well, S is 2, 4. And so we get 1, 2. All right, so nice formula, not too hard to use. and in R2 it works. But it turns out this formula works in all dimensions. And so to justify this, I want to look in 3 dimensions and see why this makes sense in 3 dimensions. And I think from seeing the 3-dimensional case, you'll hopefully be convinced that as we go up to even higher dimensions, it still makes perfect sense to do this. All right, so let's move into higher dimensions. So I have these 2 vectors here, and I want to project the red vector onto the blue vector. So I want to project 3 minus 2, 4 onto minus 6, 1, minus 1. How am I going to do this? Well, let's draw the picture. So I guess why does this make sense? Well, the blue vector that we're trying to project onto, it defines a line in 3-dimensional space. Here I've drawn it in orange. Right? When we take the span of the blue vector, we get this line. And what we want to know is the closest point on this line to the red vector. And I can drop that line here, and we see that I've dropped a perpendicular line from the tip of the red vector onto the orange line segment. And so this defines the projection, which is green right here. But it's really hard to, figure out what this is. And as we'll see, it's some kind of awful fraction. So it's nice to be able to use the formula to calculate this out. So let's figure out what this green vector is using that same formula. So here I'm projecting V onto S. The projection onto S of V is V dot S over S dot S times S. And when I work this out, here, what's V dot S? Let's actually write it out this time. 3 times minus 6 plus minus 2 times 1 plus 4 times minus 1. And then S dot S is minus 6 squared plus 1 squared plus minus 1 squared. And so in the numerator, we'll get negative 18, negative 20, negative 24. And in the denominator, we'll get 36, 37, 38. And actually, let's just write down what S is. Here, S is minus 6, 1, minus 1. And when we work this all out, what we end up getting is 72/19 minus 12/19 and 12/19. So we've projected S onto V. We found the formula for this green vector. And so we can see that this is that green vector. Okay. I want to move away from formulas for a second. Let's just zoom in on this. I think often looking at the 3-dimensional example for something tells you why this should make sense in higher dimensions. And I've drawn all these things here, and I need to choose better colors for these things. But all of this stuff is going on in a 2-dimensional subspace of R3. Right? So here, and let's choose a better color if I can. I think I've used basically all of the colors that are available. Let's see, will this, there we go, okay. Yeah, so we're working in a 2-dimensional subspace of R3, right? And so one way of thinking about what we've done in translating this to R3 is that we didn't really translate anything to R3. We said, hey, these 2 vectors that we initially cared about, right? We were initially only caring about talking about the red and the blue vector. These live in a 2-dimensional subspace of R3, and all of these other things I drew, this orange line, this purple line segment, and then this projected green vector, these also live in that plane. And so really we're just working in 2-dimensional space. And so our formula incorporates all three dimensions, but the reason that this picture makes sense, one way of thinking about it, is that we are in a two-dimensional subspace of R3. Why is this a useful perspective? Well, next I want to say, what if we're in R4 or R5? There will be situations in which it makes a ton of sense to want to project a vector onto another vector in higher dimensions, and we can't visualize that, right? We can't draw all those dimensions. However, we do know that if we're only dealing with two vectors, the span of those two vectors is a two-dimensional space. And so this sort of question about, where does a vector project onto another vector makes sense in higher dimensions because we're only concerned with a two-dimensional subspace of those higher dimensions. When we have a question like this in higher dimensions, we're not going to be able to draw a picture and visualize it. We'll just have to rely on the formula. So I want to real quickly, to finish this up the calculations, go through a calculation in R4 of projection. So we're in R4, and we want to project one vector onto another. This is V and this is S. Then our projection onto S of V is given by the same formula. As always, you may want to just kind of pause this and work this out on your own. It's always good to practice examples. What do we end up getting for the dot product? Well, we get 2 minus 3 is -1, still -1, plus 3 is 2. And S dot S is 4 plus 9 is 13, plus 25 is 38, plus 1 is 39. And so the vector we get is going to be hard to fit in the space that I've left myself. Is 4 39ths, 6 39ths, 10 39ths, and finally 2 39ths. No picture, right? We didn't draw one, but we were able to solve this. Okay, so that's it for calculations. One thing I wanted to mention before I go into, I'm going to give a brief explanation of why this all actually works. There's some other terminology for this. So we talked about, and I've used this terminology in this video already, but when we're talking, let's just go to this 2D picture. When we talk about projecting a vector onto another vector, you'll often hear this phrased as projecting a vector onto a line or as projecting a vector onto the span of another vector. These three concepts are all the exact same thing, right? If we have a non-zero vector, that defines a line in space just by taking its span. And so projecting onto a line, projecting onto the span of a vector, projecting onto a vector, as long as it's a non-zero vector, they're all the same thing. And we do the calculations in the same way. So final thing, why does this work? And it's actually pretty quick to see why this works. Because if you draw the picture, you realize that you could solve this yourself, right? So I have some vector, V, and I want to project it onto another vector, S. And so what I want to do is I want to draw a perpendicular line. I don't know why I've drawn this so small here, and I want to figure out what is, let's blow this up a little bit. I've dropped a perpendicular line. I don't know why I chose to do it like this. And I want to figure out what is this new vector here, which I'll call W. This is the projection. And what you realize is that really what you need to do is just some trigonometry. if this angle's theta, then the cosine of theta, opposite over hypotenuse, sorry, adjacent over hypotenuse, is the length of W divided by the length of V. And we also know what the cosine of theta is from our talk about angle between vectors. It's V dot S over length of V times length of S. And I'm not going to go through all of the steps here of the algebra because I don't think it's that insightful. If you're interested, you can do it on your own. But when you set these things equal to each other, what you can do is you can figure out what the length of W is supposed to be. And then you end up getting this formula for W. So we can do all of this kind of dot, 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 and we find out that W is equal to V dot S over S dot S. So that's just a real brief kind of picture of where this comes from, right? And this is a two-dimensional picture, but as I mentioned, even in higher dimensions, we're really just working in a two-dimensional subspace. So this sort of argument works in any dimension. And it also works if our angle is more than 90 degrees, right? If our vectors are kind of going in different directions. So this formula is not really some mysterious thing. It really just comes from the geometric picture of what projection is all about and our formula for the cosine of the angle between two vectors. All right, so hopefully that was a helpful introduction into what projection is and also how we calculate it.